In the last tutorial, we learned about continuous compound interest. We also learned that the solution that we came up with could be generalized to understand how anything grows over time. But things don't always grow. Sometimes they decay. And if they do grow, they don't grow forever. At some point, they stop growing. How can we use differential equations to understand how things decay or how things stop growing? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. I'm assuming that you've watched the first 4 episodes of this series, so I'm assuming that you know how to use Pluto notebooks, and that you know the basics of the Julia programming language. I'm also assuming that you know how to use the differentialequations.jl package in order to solve a simple ordinary differential equation. With that said, let's get started. Radiocarbon dating is also known as carbon dating. You've probably heard of it. It's a trope of science fiction movies. For example, an archaeologist goes out into the desert and digs up the fossilized remains of a human with a pet dinosaur, and then uses carbon dating to discover that we're all just living in a simulation. Although that may be fiction, here in the real world, we can use differential equations to solve radiocarbon dating problems to discover how many years have passed since a living organism passed away. Carbon-14 was discovered in 1940, and then in 1949, radiocarbon dating was pioneered by American physical chemist Willard Libby and his colleagues. For his contribution to the development of radiocarbon dating, Libby was awarded the Nobel Prize in Chemistry in 1960. At a very high level, here's the basic idea behind radiocarbon dating. In nature, carbon exists as 3 isotopes, 2 stable and 1 radioactive. The 2 stable ones are known as carbon-12 and carbon-13. The radioactive one is known as carbon-14, also known as radiocarbon. Carbon-14 has a half-life of 5,730 years, meaning that if you start with a container holding 100 units of carbon-14, then after 5,730 years, there will only be 50 units left in that container. In living plants and animals, the ratio of carbon-14 to carbon-12 is the same as it is in its environment. Once the plant or animal stops living, the level of carbon-14 begins to decay, while the level of carbon-12 remains the same. But it doesn't decay in a straight line. It follows a decay curve. We can use a differential equation to define how the remaining carbon-14 percentage changes over time. If we can solve this differential equation, then we'll be able to predict the remaining carbon-14 percentage at any time t. Using this information, we'll be able to estimate the age of an organic fossil. Let's see how to do that in Julia by using the differentialequations.jl package. Let's start by firing up the Julia REPL and launching Pluto. Next, let's create a new notebook and title it Radiocarbon Dating. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. Just as a reference, I'm going to add a link to the Wikipedia article on radiocarbon dating. Next, let's add a few packages. Now that everything's loaded, let's describe the problem that we're trying to solve. You'll be happy to learn that the workflow for solving the radiocarbon dating problem is nearly identical to the workflow that we used in the last tutorial to solve the problem of continuous compound interest. Just like the continuous compound interest problem, the radiocarbon dating problem is an example of an ordinary differential equation. The equations are literally the same. I'm not kidding. This Julia function is the same one we used in the last tutorial. Now, when it comes to assigning variables, the workflow is the same in that we need to assign values for u, p, and t, but the specifics here are important. In this case, u is the carbon-14% remaining, and it has a beginning value of 100%, or 1. In LaTeX, you can create a superscript by using the caret character immediately followed by curly brackets. The parameter p is the carbon-14 decay constant. This number is similar to the interest rate from the last tutorial, in that the decay constant is a rate of change. The decay constant is calculated based on the half-life of carbon-14, which is around 5,730 years. The decay constant is calculated by taking the natural log of 2 and dividing it by the half-life. I realize that this is all kind of hand-wavy. First of all, I'm telling you that the half-life of carbon-14 is 5,730 years, like that's a solid number. But according to the Wikipedia article on carbon-14, that half-life number is plus or minus 40 years. In addition, I'm telling you that the equation for calculating the decay constant is the natural log of 2 divided by the half-life, as if you know this equation. Unfortunately, I'm going to have to ask you to trust me, since the derivation of this equation is beyond the scope of this tutorial. In other tutorials that I've seen on radiocarbon dating, this decay constant is just given as 0.000121. This equation is where that 0.000121 comes from. Now that we've calculated the carbon-14 decay constant, we need to assign a value to the variable p. Fundamentally, the only difference between the continuous compound interest problem and the radiocarbon dating problem is that the parameter p is positive for growth and p is negative for decay. Next, we need to assign the values for t, which is time in years. The only slider that we're going to set up for radiocarbon dating is for the ending time, so we can adjust the time span from 1 year up to 50,000 years. And that's it. The workflow for defining the ODE problem, solving the problem, and plotting the solution is exactly the same. So this solution has a lot more timestamps compared to our continuous compound interest problem, because it's attempting to solve for 50,000 years. As you can see, the time increases from 0 to 50,000, and the values decrease from 1 to close to 0. As a sanity check, Let's look at the solution when t equals 5,730 years. Since 5730 is the value for the half-life of carbon-14, seeing a solution of 50% is reassuring. Let's plot this solution to see what it looks like. So this plot is like a mirror reflection of the continuous compound interest plot. The continuous compound interest plot started out growing slowly, and then at some point started to grow rapidly towards infinity. This plot starts at 1, and then decays very quickly initially, and then at some point the decay slows down so that it approaches 0, but never quite gets there. The x-axis is time in years, and the y-axis is the carbon-14% remaining. Let's add some attributes to our plot to make it more presentable, and to lock the values in the axes. Now, let's pull our slider down to the plot so we can adjust the time span. Let's also add some markdown to show the value of the carbon-14% remaining at any time t. As a reminder, we can find the value by using the variable named SOL, immediately followed by parentheses, and then placing the variable named t_end inside of the parentheses. You need to include a blank space immediately following the first quotation mark and just before the first $sign in order to have the LaTeX appear in line. Now when we move the slider, we can see the curve update automatically, and we can see the value change for the carbon-14% remaining. One of the challenges of using the slider with such a large range is that the slider cannot move one unit at a time. The best way to use this slider is to get close to the range that you're interested in, and then change the range for the slider to get more precise. For example, try to get the slider to year 5730, which is the value of the half-life of carbon-14. At that time t, the carbon-14% remaining should be 50%. As you can see, I can't get to 5730 exactly, but I can get close, and the carbon-14% remaining is indeed around 50%. Even Plotly isn't much help here, since 50,000 years is such a large time span. Even though half of the carbon-14 is gone after roughly 5,000 years, amazingly enough, there's still some left even after 50,000 years. But as you move further out in time, the amount of carbon-14 remaining becomes extremely small, so it becomes increasingly difficult to estimate the age of a fossil. As a result, radiocarbon dating is generally limited to dating samples no more than 50,000 years old. So how can we use this model to figure out how old something is? Well, let's say you dig up some fossil in your backyard, and you send a sample of it to a lab that does this type of work, and based on the results, you can determine that the percent of carbon-14 remaining in your fossil is 10%, or 0.1. Now, you can adjust your handy-dandy slider until you get to a carbon-14% remaining value near 0.1, and that should give you a pretty good estimate for how old your fossil is. So, based on this model, your fossil is roughly 19,000 years old. Pretty cool, right? You can always adjust the range for your slider in order to fine-tune your estimate. As you can imagine, the actual process for using radiocarbon dating to estimate the age of a fossil is much more involved than my cartoonish example. In addition, there's an ongoing debate as to the accuracy of this dating technique. There's also some debate as to the standard carbon-14 to carbon-12 ratio that should be used when testing samples. But the point of this exercise is not to turn you into a radiocarbon dating expert. The point of this example is to demonstrate at a very high level that you can use the same differential equation and the same solution workflow to solve problems for both growth and decay. The only significant difference is that the growth rate is a positive parameter, and the decay rate is a negative parameter. Otherwise, the actual differential equation and the workflow are the same. So now, we know how to solve problems for both growth and decay. But things don't just grow or decay. Sometimes, things grow initially, and then at some point, the growth begins to slow down as it reaches some equilibrium point. How do we solve those types of problems? Ever wonder why populations don't grow forever? Sooner or later, a population reaches a saturation point by running out of resources, like food and/or water, to sustain a larger population. That saturation point is different for every location. So how can we better understand how populations change over time? Pierre-François Verhulst was wondering the same thing back in the 1830s. Verhulst was a Belgian mathematician and a doctor in number theory. He is best known for the logistic growth model, which is visualized by the logistic function, also known as the logistic curve or the sigmoid curve. The logistic function is an S-shaped curve characterized by an initial stage of exponential growth, followed by an intermediate stage of steady growth, concluded with a mature stage, resulting in a slowdown in growth. This curve was the result of Verhulst's research into modeling population growth in Belgium in the 1830s. He first published his equation for population growth in 1838. In the early 1900s, American scientists Raymond Pearl and Lowell Reed popularized the equation by modifying it slightly for use in population biology work. As a result, the equation that we'll be using today is sometimes referred to as the Verhulst-Pearl equation. Back in Pluto, let's get back to the Pluto welcome page by clicking on the Pluto logo at the top. Next, let's create a new notebook and title it Verhulst equation. This is optional, but I'm going to customize this user interface like I did before. Let's save this file by using the Save Notebook bar at the top. Just as a reference, I'm going to add a link to the Wikipedia article on Pierre-François Verhulst. Next, let's add the same packages that we used in the last notebook. Just like before, let's describe the problem that we're trying to solve. Just like the continuous compound interest problem and the radiocarbon dating problem, the Verhulst equation problem is an example of an ordinary differential equation. You can display large parentheses in LaTeX by using \left or \right, immediately followed by either the opening parenthesis or the closing parenthesis. I know that this equation looks a lot more complicated than the previous two examples, but if you ignore the part in parentheses, you'll see that the first part of this equation is exactly the same as the equations for both growth and decay. The part of the equation in parentheses define how the population slows down as it approaches a saturation point. Let's add some markdown to clarify this equation. N is the unknown function that we're trying to understand. N is the population at any time t. And R is the growth rate of the population. And K is the maximum population that the environment can support, or the saturation or equilibrium point. Just like in previous examples, the differential equations package expects the differential equation to be defined as a Julia function that takes the arguments u, p, and t. But the Verhulst equation contains a couple of parameters. In this equation, I've replaced n with u, which is the unknown function that we're trying to understand. And I've replaced r and k with p1 and p2. We can use this equation to define our Julia function. Now, before you hit Ctrl-Enter, let's talk about this code. This code will work, but this function is a little difficult to read. The P1 and P2 are particularly confusing. I mean, what's P1 again? What's P2? Let's comment this code out and try a different approach. By the way, you can use Ctrl// to comment out a line of code, just like you can in other programming environments. After converting the code into a comment, you still need to hit Ctrl-Enter to execute it and to add a new cell. The differential equations package allows for several different options for defining the Julia function for a differential equation. The option that I'm going to show you allows you to use the actual variables when defining your Julia function. In my opinion, this function is a lot easier to understand. Here, we've assigned u to n, and we've assigned p to the parameters r and k. Now, we can use the actual equation in our Julia function. Next, we need to assign values for u, p, and t. For this example, let's model the population of rabbits in an ecosystem. It doesn't have to be rabbits. It could be the population for anything, really. The values that I'm using here are completely contrived for demonstration purposes and are not based on actual observations. U is the population of rabbits. But since we're using n as our unknown function, let's use a variable named n_begin for our beginning population. Let's also bind the variable n_begin to a slider ranging from 1 to 20. For p, we need to assign values for two parameters, r and k. Let's say that r is the growth rate per month. Let's bind r to a slider ranging from 1% to 100%. K is the maximum population. Let's bind k to a slider ranging from 100 to 200. Now that we have sliders for both r and k, we need to place the values inside of an array and assign it to p. Finally, we need to assign values for t, which in this case will be time in months. Let's bind the t_end variable to a slider ranging from 1 month to 72 months, which will give us a time span up to 6 years. Now that we've assigned t_begin and t_end, we can define tspan. We are now ready to define our ODE problem, solve it, and plot it. In our ODE problem definition, we need to replace f with the name of our function, which is Verhulst. And we need to replace u_begin with n_begin. Otherwise, the workflow is the same as the previous examples. Okay, let's take a look at the solution. It looks like the timestamps are going from 0 to 72 months, and the population is growing from 1 to around 200. But it's a little difficult to tell exactly what's going on just by looking at this output. So let's plot it to see what it looks like.
Ta-da!
Congratulations! You have just plotted a logistic function. The x-axis is time in months, and the y-axis is the population of rabbits. Let's add some attributes to our plot to make it a little more presentable and to lock the values in the axes. Just like Verhulst observed, the population curve follows 3 stages. An initial stage of exponential growth, followed by an intermediate stage of steady growth, concluded with a mature stage of slowing growth as the population approaches the saturation point. Let's pull our sliders down so we can use them for some analysis. Let's add some markdown to see the ending population. Now, we have a working model that we can use to fit our observations in the field. For example, we can change the maximum population to fit our environment. We can change the number of months to predict the population at any time t. We can change the growth rate based on our observations in the field. Even if we increase the growth rate to 100%, we don't get an error since there's an upper limit preventing the population growth from going off the charts. And we can change the beginning population based on a count that we measure in the field. I think that this model really demonstrates the power of a numerical solution to a differential equation. With just a few lines of code, you now have a fully functioning, highly customizable, interactive model that can be used for simulations and for analysis. And on top of that, it costs you nothing. Amazing, right? So, what have we learned today? The workflow for solving differential equations that we established in the last tutorial can be used to solve many different differential equations. The key to solving these equations in the differentialequations.jl package is to understand how to translate the so-called LaTeX equation into a Julia function that the differential equations package can understand. Once you've figured out how to do that, then the rest of the workflow to define the ODE problem, solve the problem, and plot the solution is exactly the same for every problem. There are many more examples of differential equations for us to explore, so stay tuned for the next exciting episode. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, please consider making a purchase at the Doggo.jl online store. You can browse through a wide selection of Doggo.jl merch by clicking on the Store tab. For one-time donations, please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. Early access videos do not contain YouTube ads. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.